Yuri and I back for common questions number 5. So let's just walk through some of these things. We're getting less into stuff that we can just memorize on a sticky note and more kind of analyzing questions. With lake effect snow, okay? So I don't have anything to draw here, sorry. Lake effect snow, the wind just needs to blow over a lake. The longer that it blows over a lake, so like right here, if it was blowing across the lake this way, that wouldn't be the longest part of the lake. It wouldn't pick up as much. But when the wind starts to blow across the lake this way, it can pick up more water. So the lake needs to be a little bit warmer than the land, so water can evaporate over the lake and then get dumped off. So make sure that's working there. The wind needs to blow from the west to the east across the lake, and that's how you can see it getting dumped over here. That's why we get a lot of lake effect snow, and then this other side of Canada doesn't, because the wind doesn't blow that way. These questions, there's not one specific thing to show you. These are kind of difficult. You got to mentally picture. Sometimes I like to draw on this. You've got to see when the rain falls, what's the pattern that the rock underneath, the bedrock, would make the rivers flow, okay? So number 1 would be like a flat area. Number 2 would be an area sort of like a volcano where everything is flowing away in even directions. Number 3 is tough to even picture. It would be like a ridge where you've got a bunch of rocks like this, and the rivers would be flowing parallel to those ridges. And then number 4 shows it going around a volcano or a raised up area and down. So number 4, you can see how these rivers are flowing around the shape of the bedrock. So the bedrock underneath controls that. And it's really kind of, you've got to analyze each diagram to do that. So we'll practice more of those in class too. ESRT page 5, look up hot spots, and there you go for that one. Cloud formation, Rec Schweck, that's been in a ton of videos. Same thing with energy production and stars, crossword clue with the sun. All of those things, you need to you can go back to those other videos for those informations. Anything to do with water, okay? So when you see the word joules, this is how much energy it takes up to heat up water or other materials. You can see that other things take less energy. That's why they heat up faster. But also the properties of water. Anytime you see the word joules, energy gained or released, melting, freezing, vaporization, condensation. This is how much energy it takes to make the phases change. So if you're seeing a phase change of water, gaining energy or releasing energy, more and less, look at these numbers here. So water in joules is in one of these 2 diagrams. That's on the front of your ESRT. Rotation. Rotation is the spin. Daily changes. Anything you're seeing with rising and setting, a day-to-day change or hour-to-hour change is a rotation. Long-term things are revolutions. So if you're seeing things happen over the course of a month or a year, it's a revolution. If you're seeing something happen in one day, it's almost always a rotation. Sun paths. So let's just draw a sun path diagram and analyze them a little bit. There's a bunch in our ESRT, or in our review book, I mean, not our ESRT, that we'll be going over too. I can break those out in a second too, if you like. So we saw this outside too. When you're looking at these diagrams, okay, when something rises right in the east and sets right in the west, that's going to be March or September. And then you've got to remember, from March, April, the sunrise is going to be here. May, and then June, the sunrise gets the highest. Like that. And it changes by 23.5 degrees each season. From season to season. Because that's the tilt of the Earth. Tilt of the Earth is the reason for seasons. That would be 23.5 degrees. Okay. And then June, July, August, your September sunrise would be back here. And then it gets lower in the sky. October, November, December is going to be a much shorter path. And that changes 23.5 degrees again. So it's a 47-degree change over the course of 6 months. So parallel lines going up and then going back down. Shortest days are in the winter, so that's why the line is shorter. Longest days are in the summer, and the line's longer. Okay, we'll be going over those diagrams more. We'll spend a whole day on them, really, most of a day. But if you look in your appendix in the middle of your review book, they have all sorts of different diagrams, and it tells you. So, like in the southern hemisphere, the arc is tilted the opposite way. In the northern hemisphere, this would be really far north because the sun is out all day long on this one, 66.5 north. One like we just drew here. So it gives you the latitude and it gives you the date and it tells you some information about them. So we're going to spend time on these in class, but you also should look through these and kind of make sure you understand how those sun path diagrams work. They're pretty common on the final. Tides. So here's the thing with tides. The tides go up and down and up and down and up and down, okay? And it's 12 hours from high tide to high tide and another 12 hours to the next high tide, okay? It's actually a little bit more each time. So in one whole day from here to there, it's not just 24 hours, it's actually 24 hours and there's an extra 50 minutes to go from high tide to the following day's high tide, okay? Your diagram, I put this on here because I wasn't super happy with this diagram when they put it on the test. It's a little tricky because it seems like it's showing the whole day, but it's actually only showing like half of a day, which it doesn't get you to all the way the following day. So when it's asking when the next high tide will occur, here it's not, from one to the next. This is only showing you, I don't know if you can see what I'm pointing to there. This is only showing you half of the picture. It doesn't get you the full 50 minutes. Okay, so just make sure you're paying close attention to what they're showing you. It's a 50-minute change from day to day. So high tide to low tide is a 6-hour change. And then low tide to high tide is another 6-hour change. That's a 12-hour plus a little bit more. And remember, this was from the last number 4, Regents review number 4. Wherever the moon is, that's where the high tides are. And 90 degrees to that is where the low tides are. So if the moon is in a different spot, high tide always lines up with the moon. The sun helps it, but the moon controls it. Looks like the image of the moon isn't loading for mine. So with moon stuff, I'll double check if that image works. Here's the Earth. Here's the sun. If the moon is here, okay, I overcolored that a tiny bit. If the moon is there, okay, this would be a new moon. And what I do is I cover up the far side of the moon. I can't see any light in this situation. That's a new moon. If the moon is over here, okay, this is all lit up because that's facing the sun. And if I cover up the moon like that, there's a sliver of light on the right. So this is what I would see in this situation. From Earth, you would see the moon looking like this. If I go like this, or this, or this, these are the different phases they'll ask you to look at. The side not facing the sun is always the dark side. So I'll say it right here. So I'm covering up the far side of the moon. I can only see the half of the moon that's closest to me. Do you see how on the right there's a lot of light, and on the left there's a little sliver of darkness? From Earth, on the left there's a sliver of darkness. That's what I would see from Earth. This is called a gibbous, okay? This is waxing because it's getting larger and larger and then waning on the backside. So you cover up the far side of the moon, light on the right, more than half. That's why it looks like that. Let's do one more of these. In this situation, okay, if I cover up the far side of the moon, I've got to be on the Earth looking now. So this is darkness on the right. You've got to put yourself on Earth looking. There's a sliver of darkness on the right. So how does that look from sliver of darkness on the right? It would look like this. That's how that moon would look at this position. It would look just like that at this position here. One of the trickiest things for people to wrap their brains around. I know it's tough. Make sure that you ask to go over those moon questions more if you need to. Circulation around lows. Just remember, when you draw the L, this video is getting pretty long. You draw an L, that's the way that the wind blows around lows. Draw an L counterclockwise. 12, 11, 10, 9. You got that. Wind blows from highs to lows. Wind blows from highs to lows. That's the way it goes. So it goes counterclockwise and in to the low. And anything with a high, you just flip-flop. So if you can draw the L, wind blows from highs to lows, that gets you both parts of that. The one-word name for the front that just passed through New York State, well, that hurts since we can't look at that image, but I remember the image. So there's just 4 types of fronts. You have to look it up. Warm, cold, occluded, or stationary. The one that just passed New York State. So just remember, if the front looks like this front used to be here, and it's moving the direction that those shapes point. Okay, what do you think, Yuri? Oh, fossils, man. It's only section 6 or 7. You guys have a tough teacher. So, what 2 layers of the record is missing? Oh, between which 2 layers is the record missing? Okay, so you've got some erosion in different spots here. You've got erosion happening right here. That's called an unconformity, so there's missing time. Or you've got erosion right here. That's an unconformity, missing time. And I'm just checking that both of those answers weren't on there. What organisms existed when sediment in layer A was deposited? Oh, so ESRT, look up mammoth tusks and then look up the other organisms by these names. Which ones were around when mammoths were around? So ESRT in front of me. This eats up a lot of time, okay? But you look up mammoths and you see what other organisms over here were around when mammoths were around. Compaction and cementation of plant remains. Anything to do with what rocks? You look over here and you find compaction and cementation of plant remains. ESRT, page 7. Epoch, geologic epoch, that's page 8 and 9. Look those up. Looks like that's an easy question. I missed that, I guess. There's a little video here for you to watch that goes through porosity, permeability, and infiltration. This is quite the assignment. Going over this makes me realize how long this must be taking you. I'm going to give you some extra time in class. What tube has the highest porosity? So 3 different things. Porosity. How much empty space is there in between all of these rocks? And you would not think so. This is counterintuitive. But red, yellow, and green all have the exact same amount of empty space, which is really weird to think about. If you fill up a swimming pool with golf balls, baseballs, or bowling balls, and then you fill the rest of that space up with water, they actually, since they're all round, they take up the exact same amount of space. Doesn't seem like it, but it's true. If you mix them up, that's how you reduce the space. Permeability. How fast can the water go through? The bigger particles like this over here lets water go through faster. So that's higher permeability in the green. And then capillary action, which one stays the wettest? Red is going to stay very, very wet. So would this mixed sediment over here. But the smaller the particles, they stay wet longer because there's more surface area. We're going to need to spend more time on that in class too. Make sure you ask me questions on that. I'll be giving you a little extra class time on this one. This was pretty long. Good luck. Yuri says, I can't tell what Yuri's saying.